ज़्यादा बढ़िया चलेगा। देखो लाइव नीचे करना पड़ेगा। हाँ,
Hello, Dr. Anish. How are you?
Good afternoon, sir.
Good afternoon.
Audible. Yeah, everything is good, sir. How about you?
I'm fine. बस 2 मिनट और वेट करते हैं, कुछ पार्टिसिपेंट और ऐड हो रहे हैं.
Okay, sir. Actually, there's some problem with my video. So video वो फाइन रहेगा कि अगर सिर्फ ऑडियो में
हाँ, नो इशू. स्क्रीन शेयर तो हो जाएगी ना आपकी?
हाँ या
ओके, नो इशू.
Sir, I'm sharing my screen. Please let me know if there is.
Okay. Tanu ma'am, please start.
Okay, sir. Good afternoon, all the directors, HOD, faculty members, research scholars, students from different colleges. In this afternoon session, our speaker, Dr. Anish Malan, we are thankful to you, sir, for giving us your valuable time. Good afternoon, sir. I, Tanu Saxena, Assistant Professor of Engineering Department, welcome you on this STC on solar energy, a pathway to green energy. Dr. Manish Malan, currently working as an assistant director in National Institute of Solar Energy, he has published 8 research papers in international journals and conferences. He is pursuing PhD from IIT Delhi. Overall, he is the shining star in the field of solar thermal energy. I request you, sir, kindly share your thoughts with us. Thank you so much, sir, once again.
Thank you very much for the kind introduction. And I'm just a beginner. I'm not a shining star. Like we are trying to be. So hope my screen is visible to all.
Yes.
Yeah. Okay. And the slides are changing too.
Yeah.
Okay. Okay. To begin with, today my topic of presentation is on solar thermal technologies, consistent systems. That like in this will be mainly like sharing some thoughts and ideas regarding how solar thermal concentrators works and what are the domains like in which solar thermal technology may be fruitful or like how like the further research topics can be carried or like, can be performed in this particular field. So just the outline of the presentation is as follows. So we'll deal with introduction, just classification, then we'll start with non-concentrating collectors, that is flat plate evacuated tube collector, and then gradually we'll jump into the concentrating power system, which consists of PTC, LFR, central tower, and parabolic dish collector. So just the complete presentation will be sort of introduction only, not much in details. But then my main objective for this presentation is just to let you know about the various system and how those system has been developed. So if we talk about solar energy system in general, like we know there are two particular routes, solar photovoltaic and another is solar thermal energy systems. So solar voltaic mainly utilized for power generation perspectives, And solar thermal energy system have certain routes, but the end product is either the process heating or the power generation. If you have viewed like the water heating systems and that solar thermal power plants, so those will fall in the category of solar thermal energy systems. So in this section, we'll be only dealing with the solar thermal energy systems. Uh, just as an overview, how the system works, very simple like block diagram is there, how the energy that we are harnessing from the sun can be utilized. So first, the thing is, suppose we have a sun, like from the where we are getting the energy in the form of radiation being diffused. Are the two components that compose of the complete radiation that is coming from the sun. Then that energy, whatever it is coming, we need to collect it. Then only we can able to utilize in for any of the purpose. So for the solar thermal systems, will be here we are categorize those things into solar thermal collectors or concentrators. Because we may be using non-concentrating ones, so for that we are only using the terminology collector, and for the systems that are using concentrating and like tracking systems, those we are will be using the terminology concentrator for them. So once these collectors absorb the radiation or absorb the incoming radiation onto the receiver, so we are having a hot receiver section at our side. So the next step will be we'll be using some heat transfer fluid in order to evacuate that heat from the collector. So the this will fall in this category. So any heat transfer fluid can be utilized, for example, for low temperature applications, water heating or so. So we directly use water. And for other just like power generation, in which we nearly need a high temperature or somewhere around 300, 400 or 500 degrees Celsius. There we work on synthetic fluids. So this and then like up to this point, we have harnessed energy. We have now energy available with us in the form of heated fluid. Then we can directly use this heated fluid for our application, that is either heating or cooling if we are talking about only the process heat, or like if our temperature are enough, we can go for the power generation part. So the both the end product will be like if we are using open cycle, we'll let down the fluid into the environment, or we'll be making that exit from our room, and again we'll be using a fresh heat transfer fluid. In the case of water, generally this is the scenario. But if we are using synthetic fluid that for very high temperatures, so then we don't only work on open cycles. We work on closed cycles, and the same fluid will be heated back again through the collectors and will send in the cycle again. Now the thing is, what then this thermal energy storage systems is for. So the idea behind that is maybe you are having a heat requirement. So whatever you are generating from the collector is more than what is required for your heating cooling application or for the power generation. Then in that case, what you will think of maybe I can store this extra heat into my thermal energy storage, and later on when sun is not there, because we are having the sun for a fixed number of hours only. So in that duration, the energy that we have stored in thermal energy system, we will be using either for heating application or the power generation based on our requirements. So sometimes this thing deliberately also we do like for the power generation plants, like where we can't just construct a plant for a working hour of 8 hours only, in which we will be having sunshine. Okay, because our capacity utilization factor will drop down. So what we want to do is we want the whatever the energy we can generate in that particular amount we generate, we'll store that into thermal energy storage, And then again, like after 8 hours or so, in which like late evening hours post 5, when there is no sunshine, then we can use that energy so that we can extend the working of our plant for as much as hours we can do. Either we can go for 6 hours storage, 8 hours storage, 10 hours storage based on the cost requirements of it. So this is the general view of the solar thermal energy system. Like in whatever the system you'll see, you will only find these particular components. So next, we'll now sharing some details on the solar thermal collector. Okay, we know about collectors. So how can we segregate them? How can we distinguish between like what kind of collector will fall in what category? So first thing here will be we are dividing just on the basis of whether it is concentrating or non-concentrating. So जो भी like whatever there in the non-concentrating part, that is fat rate or etc, there we are not using any kind of uh, tracking system. Like these will be only static standalone system provided in one particular direction will fix it. The pictorial representation of those will be sharing in the later slides. Then now after the non-concentrating part, we'll jump onto the concentrating part. So here then, or based on the tracking, what kind of tracking we are using, we can still distinguish them on the basis of whether we are using single axis tracking or the dual axis tracking. In case of single axis tracking, there are three major concentrating collectors that have been used across the world. That is compound parabolic collector, parabolic trough collector. Mainly, you may heard of the PTC for that. Linear Fresnel effector, LFR. Okay, so these three come under the category of single axis tracking. Now, in the two axis tracking system, we have a parabolical dish collector, uh, generally donated by PVC, and the another category is power tower. So now, like, why we need to distinguish them? So, like, maybe you just want to know about like, what kind of applications we can deal with them. This is also one criteria in which we would like to classify them. As here we are seeing that is non-concentrating. So there, like it's the common depiction will be like it can be only used for the low temperature application, that is less than of 100 degrees Celsius. That's why we have discretized those. And in concentrating, we can go from 200 degrees Celsius to somewhere around 600, 700. Like above then is also possible, but as of now, we are mainly dealing with such temperature ranges. That too, the maximum we can achieve here in dish and tower, and for like here will be some dealing somewhere around 200 degrees Celsius, here up to 395 degrees Celsius, and here also somewhere around 250 degrees Celsius. So these are the different temperature ranges and the classification of the solar thermal collector. So now, by just this brief introduction, you may able to aware like if the temperature range, like whatever the application you want to deal with. If it is less than 100 degrees Celsius, you may be more likely to use non-concentrating collectors, that is flat bed collector or evacuated tube collector. In this category also, flat plate collector generally give a temperature, utilize for a temperature range of 50 degrees to 60 degrees Celsius only. And it may go up to 120 degrees Celsius, like some study reports that even higher temperature range is also achieved. But generally, for the temperature range for this particular time, like, will be somewhere between 8 to 20 degrees Celsius. So these are the pictorial representation of the collectors that we have discussed from the previous slide, and along with the what kind of temperature and in which temperature range we can work with this particular type of collector. So this flat plate collector, pictorial presentation is shown here. You may have seen this system in the rooftop of the houses that have been, or the rooftop of your hostels, in which like these are basically used for water heating and as a kind of replacement of the geyser. Another thing like evacuated tube collector, something like this. That earlier, what I have said about this water heating system. Earlier, the major market share is for flatbed collector, but now these days that has been shifted to evacuated tube collector because we are getting more efficient, more higher efficiencies, and will be able to have higher temperatures also. So gradually, from flat plate collector, it has been moved out to evacuated tube collector. So that this is a journey for the water heating application with having a temperature range of less than 100 degrees Celsius, or here it is somewhere around 120 degrees Celsius. That's what we have mentioned in the previous slide. So in now we are jumping into the concentrating collectors. So first thing, maybe if you have studied something related to the solar collector, you may have heard something like this. Like this is a flat plate collector. Okay, and if you will be uh, using that for like you will be having something like these structures on it, so it may be appear as these booster mirrors also, that further may able to increase uh, the working temperature range of the non-concentrated. So this the similar very concept has been utilized when we'll be working with the compound parabolic collector. So here in this picture you are seeing the CPC collector. So you will be seeing one parabolic curve profile will be there, and in the center, a CPC collector has been used. So how it has been made? So the thing is, the axis, like these two parabolic curves have some shaded region here. This where the receive, or you may say it's a receiver section that is utilized for where the receiver will be held, and these two are that parabolic curve that have a different axis. So earlier in this, what reflector mirrors, or some that reflector booster mirrors, sometimes we say like these are not the ideal parabolic shape. So that how that it is different from the flat plate corrector with booster, and the differentiation with the compound parabolic corrector. So it will be generally will be something like this. So this will be a flatter surface. This is one parabolic curve profile, which having a something axis there, and this is also a second parabolic profile, which having something axis here. So the thing will be like these cross section. Now what we are receiving in on the upper section. This is now the area, or the aperture area, you may say, like that is the actual aperture area where the solar radiation can be received, related to what we are only getting like this much on the receiver section, that what we are getting in case of non-concentrated. So so that's why it only gives a temperature range of somewhere around 150 degrees Celsius, because it is not completely concentrating. But yeah, for achieving very high temperatures, the height of the collector will become something like this, which is practically not possible. So that's why these type of CPC are generally utilized for low concentration ratios. Like I I use a term concentration ratio in the lateral slide. I will tell like how to compute this. So the CPC, okay, first we'll talk about concentration ratio only. So this is the like ratio of aperture area. This the AP I'm denoting with aperture area to the receiver area. Then what aperture area denotes here is, aperture area is the total area in which the radiation is being accumulated on the receiver. For example, for flat plate, this is the aperture area. Okay, and you may be surprised to know, or maybe it's a common sense also, that the receiver area is also the same for this particular section. Okay, so here what the concentration ratio will be, like this is also same, this is also same, so flat plate collector it will be 1. So, but like in the case of CPC, like if you see now, this is our aperture area. We can denote it by AP, and this is our receiver area, only this particular section. So it's quite clear from here that here the denominator is higher as compared to denominator. So here CR will be greater than 1. So this is how we define the concentration, like whether the collector is a concentrating type or non-concentrating. So here we in the CPC we only deal with the maximum concentration ratio of 5. Now, further category to this, like here, as we are seeing that temperature range is about 400 degrees Celsius. So their concentration ratio must be high. Okay, and here concern in the point focusing solar concentration ratio should be more than what we are achieving in these particular concentrator. So I am skipping these two part as of now because a detailed explanation will be there in the later slide, and I will be using that. That will be more useful to get the insights of those. Now, just a basic procedure for the solar thermal collector, how one should deal with that and how one should design. Like this design or the procedure that I have listed here is just a glimpse of some of the parameters that will be associated with most of the like concentrator or the solar thermal system. There may be some another topics or another procedures as well that needs to be considered, but these are those procedures will be subjective to some specific solar thermal system. So here we are talking about in general of solar thermal system. So first thing is uh, it is applicable to any of the application and any of the design perspective. So first and the foremost thing is you need to identify the application. For example, you want to install a solar concentrator. Okay. Uh, then what you will be looking for? How much temperature I need? What's the application pertaining to that solar collector that I will be using? For example, if I need hot water at my home. So I may be seeking something like, oh, okay, I will have the collector that will give me some temperature somewhere around 50 degree or 60 degree that may be sufficient enough for bathing purpose. So that's the for that particular application. So you will now will be going for the further process. Okay, then now I identified some one application that is the bathing purpose. I need a hot water. So for that, I may need the flat plate collectors. Okay, that may serve the purpose. Or if not, then I may also seek for evacuated loop collector that we have discussed in earlier slides. That will be decided on the basis of your temperature requirement. If your temperature, here we are discussing this slide on the for the water heating purposes. So now you have identified the application that you need hot water. Okay. Now in the next step will be, okay, you need a hot water, but what should be its temperature? Like what's the temperature range you are looking for? If that will help you decide the uh, your collector configuration or the collector that you will be using. Okay, here now if you have seen work with that and you have identified that my temperature requirement will be somewhere between 70 degree to 80 degree. Okay, so the next step will be you will search for the suitable technology or what kind of solar thermal collector will give me a temperature or somewhere between 70 degree to 90 degree. Then you may come with some options like these three options are there. that may give that much temperature. Then the further step will be you may seek for the availability of that particular collector that you have shortlisted for your particular operation based on the temperature range. So whether those are available in the local market or not. If they all are available, then it will be purely your choice based on the selection of technology, because here you have shortlisted based on this temperature range. For example, if I talk about this temperature range, so you may have two choices only. One is ETC collector. Okay, and the mostly and to a higher extent, you may see compound parabolic collector. You may not go beyond that because this can use up to a temperature range of 150 degrees Celsius and this of 120 degrees Celsius. And the one that we have skipped, that flat plate collector. So this I have skipped because it gives a temperature of maximum somewhere around 50 degrees to 60 degrees Celsius. So based on the availability and your requirement, then you will choose your collector configuration. Then based on the volume of the hot water you will be requiring, you will find out that the what will be the solar field area will be required, and that solar field area mainly comprise of the collector, the complete collector area that will be uh, using for our purpose. So once that solar field area you will be you calculate that, then based on that you will find out how many of collectors will be required. Then further step will be in which orientation I should place my collectors based on the shading or the trajectory of the sun path. We will consider that. Then sometimes there are space constraints also. For example, the ideal condition for any of the solar collector is to place to south, but there may be the building orientation is such that we are only it is some that we can only place it somewhere in southeast direction. So that's a constraint to us. We have to consider that, and then all the calculations will be affected accordingly. Then after that, we'll be working with series and parallel combination based on the temperature requirement and the space constraint. And after that, we may calculate the performance of the collector, and we'll see how the designs or like how well we have designed our solar thermal systems. So any questions till now, or is there anything that I need to work on, whether speed or language or something? So you can answer. Sir? Okay, I will consider it as a no. So we'll move forward. Now, the first category that we are dealing with will be the flat plate collector. So this is the schematic of the flat plate collector. That can majorly consist of that there will be one glass cover will be there. Then this blue color, the surface that you are seeing is the absorber plate, and there will be some pipes will be connected beneath or embedded into the receiver so that you can collect your heated fluid. So that you will be seeing two openings. One will be used for the input, and like another will be used for the output of the water from the plant. So these in order to avoid the heat loss from the system, so the some insulation material is used in order to like in order to mitigate the convection and radiation losses to the environment. And then all the system is placed into the outer cover so that we can protect it from dust and moisture from the atmosphere. So this is the very simple system and being used from many decades, and is a well proven one. And sometimes you will also heard the terms selective coating for associated with flat plate collector. So the selective coating is nothing much like, for example, if we consider one surface, okay, in which that is heated up. So what we want, or like any radiation is falling on that surface too. So what we want, like whatever the radiation is falling onto this surface, it will absorb maximum of the, and the emission of the radiation from the surface should be low. So this is like what the purpose of selective coating. It will increase the absorptivity. It will increase the absorptivity of the surface, and will decrease the emissivity from the surface. Like the losses will be decreased. So that's the purpose of using selective coating. Generally, two kind of configuration has been explored or utilized. One is the parallel flow configuration, and second is the serpentine flow configuration. Second is the serpentine flow configuration. So, but mainly this parallel flow configuration you will see. So, anyhow, the temperature will be higher in the case of serpentine configuration, because here will the that our working fluid will be, or the heat transfer fluid will be in contact with the plate for longer duration of time. So heat transfers will be better here, but because of the complexity of the system, so these are not generally used. Mainly, Beller for configuration has been used, and like at the start of the session, I have used one term like the beam and the diffuse component of the radiation. Like, if you are aware of the solar incoming solar radiation composed of two components. One is beam component and one is diffuse component. So the basic idea behind that is just a minute. Uh, Hello, hello.
हाँ हाँ यस.
Sir, I have just give me 1 minute time. I have some issue with the video, so my presentation. Just give me 1 minute, sir. If
Okay.
that is okay with you. Hello.
हाँ यस.
Yeah. Okay. Uh, okay. So we are discussing regarding like the diffuse and the beam component. So, like if you see the diagram or the left hand side of the screen, there what you see, like some like component of the radiation is directly coming, like it is not deviating from its path, or that means like it has some specific path associated with it. So this kind of the radiation component of the solar is some named as beam component or the direct component, and some part of the radiation that is coming in some of any of the arbitrary direction. For example, because of the clouds, if the radiation first come here and it will have some deviated path, something like this. Okay, and or it has some deviated path, something like this. And from here, for example, you may consider it as Earth, and from here also it may reflect back to the radiation. These All these radiation components which have some different arbitrary direction are associated with the diffuse component. Okay, these don't have any specific direction associated with them. So this flat plate collector entertain both, like whether the radiation has some specific direction or not. If it is falling on the surface of the receiver surface, it will going to absorb. So this is the kind of beauty of the non-concentrating collectors, because uh, here you no need to worry about like whether I am only working with some specific kind of solar radiation. Hello.
Yes.
Just a minute, sir, it's hanging again. Sorry for the disturbance.
So, first thing I wanted to ask, like, is there
Please unmute your mic.
Okay. Sorry about this disturbances. I actually have some problem with my internet, so it's getting stuck in between. Okay. So I'm audible now, sir? Fine.
Yes, audible.
Okay. Okay. So further on, let's carry out our discussion on the solar water heating systems. So these are just the two configurations that I have represented here, that like natural convection and the forced convection. So both are associated with the solar water heating system, and it is applicable to the evacuated tube collector as well. So in the natural convection, the only thing is we'll be using one tank, and there will be no circulating pumps we'll be using because of the thermal siphon effect only. This will work on. And for the forced circulation, like we'll be using some circulating pump. So, and another thing is such systems we can use like when we don't have the sub-zero temperature ranges. Like if the temperature falls below to 0 degrees Celsius in some environment. So this kind of system will not work because here we are having the same working fluid, and that too works on the open cycle. So there is a chances that it will freeze up. So in that particular situation, forced circulation systems has been used because here like the thing is the system are closed, and very minimum they have impact from the environment, and if they do have that, we may use some anti-freezing like additives with heat transfer flow so that it will not freeze up. Okay, so that solution will be provided in this so that our collector will not we get the water inside that will not freeze up, and that later on in the external heat exchanger we can circulate that the fresh water and to get the hot water from this using shell in tube type of heat exchanger. Okay, so the another category is the evacuated tube solar collector. So generally now these are being utilized for the water heating purposes. And the thing is like they are like instead of that flat bed collector, you may able to get the high temperature. ranges here. I'm not getting into the details of why the high temperature is like how why we are getting high temperature out of these kind of collectors, because that may further increase the time and not within the context of today's presentation. The thing is, like how this evacuated tube collector looks like. There will be one header, in which like will be having entry from the one side and the output from the outside. Now the this header will be joined with some tubes. Okay, so there may be two different type of configuration in here, here too, like maybe heat pipe based or tube in tube pipe based. So that also we'll discuss. So this is a kind of heat pipe based concentrator, means in this in this pipe, like that is connected to the header. In this we'll be having some like heat transfer fluid that have a low that have a very low boiling point. Okay, so when the solar radiation is absorbed on the surface, it will heat it up, and the heat transfer is provided to the tip of the section. If you consider this is the tip of the section. So how it may look like is something like this. So these are the probes that are connected with the tubes, and from here we'll be having inlet water and here output. So water will get in contact with these section in the heat pipe, and will be having hot water at the output of the section. So this pipe will be something like that. We'll be having one absorber plate here, and this pipe may be attached on the surface of the absorber plate, or maybe this will be a part of the integrated something like this. This will be a part of integrated with the observer plate. So it will be considered as a one unit. So this concept is very simple, like that of the flat plate. We'll be having radiation. So uh, that will it will increase the temperature of that working fluid, and that is transferred to the header, and from header we can collect our uh, hot water. So now here this I want to ask, will there be any effect of the diffuse radiation here? It will be able to work on both beam and diffuse, or it will be able to work on beam only? Anyone from the participants or the audience who are listening? Will there be any effect? Okay. So, like that of the flat plate collector, there will not be any distinguish between, it will not distinguish between whether the radiation has some specific direction or not. So, whether it's a beam component or the diffuse component, uh, it will work with both. So, in collection, it will receive both of the radiation components. So, uh, this is the working of the evacuated fluid collector, heat pipe based collector fluid, that what we have discussed in the previous slide. Radiation will be collected, and the heat transfer fluid that we are having in this uh, heated pipe will get heated up, and the vapors will be absorbed at the top section, and this part will be enclosed in the header, where the water will exchange the heat with this particular surface and will be heated up and can be evacuated. So another kind of configuration for the evacuated tube collector is tube in tube type. Okay, like here, the heat transfer fluid is not directly heated up. Okay, the tube is heated up first, then water is not flowing in the tube. There is no path here to be flow. So it is flowing directly in contact with the probe. But in this type of configuration, what we'll be having multiple tubes, and the tube will be passed through this tube itself, and it will be heated up, and likewise we'll be having multiple tubes. So the single tubes that will be passing on to the multiple, and this will be enclosed in the header section. So the thing here will be having a cold water, and like this pipe that is heated up, it will pass on the heat to the water, as in heat transfer fluid, what we are working here, and it will heat it up and will rise and will be evacuated back from the system. But such type of system have certain limitations. For example, like if some of the tube will break out in between, for example, uh, like this tube will break out in between. Okay, and okay, now so the section is there. This tube has been broke down. Okay, the tube is exposed, and this surface of it is broke down. So here, what will be happening? That the water will not go to the further section of the collector, and it will lost here itself. The leakage will be here. So, which means that if in our system, like if this is a complete system with, for example, 4 5 number of tubes, any of the tube is broken down in between, so the complete system will shut down. Okay, but such problem is not there with the heat pipe based ETC, because if here, like we are getting in contact with probe, so there will not be any kind of leakage if in tube, for example, this tube breaks down in between. So there will not be that much effect on the system, and there the system will still going to produce some output. Okay. So this is the basic difference between the heat pipe based evacuated tube collector and the piping tubing tube based evacuated tube collector. Hope this is clear. So till now we have discussed about these. Now we'll be jumping on to the concentrating collectors. The first category that we'll be seeking in the concentrating collector will be a single axis vacuum system. So this is the same slide, but this it is for the recapitulation. Like what the temperature ranges now, we'll be seeking, we'll be trying to find out like where we can work. So now we'll be dealing with these three. To start with, we just need to have a brief introduction about that how these concentrators will work on, what kind of configuration and what kind of shape they will be having. So for that, like just for the information maybe so this parabolic this concentration collectors, all of the concentration collectors have one single common thing. Like there may be another, but the major common thing is the shape of the collector uh, a parabola. It will be a three-dimensional parabola or a two-dimensional parabola. So in the concentrating part, so we have first seen the like back during our elementary education days, we have heard of this property of the parabola, that when the radiation will be falling on the like on the parabola, it will direct them to the center of the receiver. So this property has been utilized in all the concentrating collectors. So all of them will be working on the same phenomenon. So now from this, and based on our earlier based on my earlier explanation about the beam and diffuse component, so will it be able to work on diffuse radiation? No. So the answer is no here, because of the property of the parabola. So it will now only able to use the radiation, incoming radiation, that like if this is the axis, so whatever the radiation is parallel to the axis of the parabola, that only will be entertained for the power process heating or heat generation or the power generation and any other application you want to do. So this is the one limitation I would say for the concentrating part, because it only work on the beam component. Okay. So that is clear now for the case of the concentrating part. Now, there may be two different type of collector configuration that I said. Like it may be 2D, it may be 3D. Okay, and there is some concentration ratio, like what we mentioned that time, that CR is the ratio of the aperture area and the receiver area. So here, if I point on to this particular diagram, this is the aperture area of the 2D profile, as we are mentioning 2D profile. And this particular section here, this is pointing out to be AR. So now it is clearly visible, I guess, that there is a huge like gap or the huge ratio difference between the aperture area and the receiver area. That's why here we'll be having more energy associated onto a small receiver section. So that's why we are ending up with higher temperature in case of concentrators. But there is still it's nothing like we can go we can increase the concentration ratio to very extent. No, it's like big no, because of the thermodynamics and the law associated with the heat transfer that restrict this to some particular extent. That is for the parabolic curve that are not like the 3 dimensional. I will say only 2 dimensions. So there, the CR can be maximum up to 200. Okay, this is also ideal scenario. In the actual scenario, the 2D concentration is maximum utilized up to a CR of 80. Okay, so then again will be if now the thing that I'm talking about, this 2D and 3D part. So the profile will be same, but in this that the particular section, this if we see this part. So if we rotate the parabolic profile onto this axis on the axis of the parabola, it will give a three-dimensional parabola. You may see something like dish antenna on your like on the rooftop of your home. The similar structures appear something like this. Okay, this will be some kind of parabolic profile, and somewhere the receiver section will be there. And that is mounted. That's a kind of a 3D parabola. So, and but for the 2D, what we do, we try, we what we do, we extrude the parabolic profile. That extrude means like orthogonal, like the perpendicular to the parabolic shape. We'll extrude it. If we extrude it, will go something like this. Okay, the shape will be 2D, and it will go something like this. That is the basics for the formulation of the 2D like 2D axis tracking or the single axis tracking system. So maybe from this animation it will be more clear. Okay, so how it has been worked, like it is a 3D profile, so the complete revolution will be there, and it is exclude. Okay, so the same system now. If you remember from the earlier slides, we have talked about 4 kinds of such systems: parabolic rough collector, linear Fresnel reflector, uh, dish collector, and the power tower. So all four are a part of these two profiles only. One, the LFR and PTC are a part of this particular profile, and dish and power tower are a part of this particular profile. So likewise, how now we can arrive at this particular LFR and the PTC PTL? So first thing will be this particular shape is the LFR only. No, sorry, PTC only, and that receiver will also be there that you may able to see in the coming slides. If now the same profile has been used to provide the configuration of the method, which means that if how it has been like we have discretized the profile something like this. Okay, that we have placed that on ground. Okay, now it's not be a complete profile. There are some sections of the profiles are there. And after that, if we exclude this, it will form uh, a structure that is very near to the ground, but is a flat in profile. But overall, if you look, the profile is of parabol. Okay, so these such systems are known to be as the linear flat. Okay, and how they has arrived now, you may see like the distance is not same as it is here because it is not the similar one, but this section is a part of very large parabola. For example, in that large, we only consider this section which is a flatter one. So for that we have discretized this angle that has been used. The similar story is with this one. This is a dish collector, parabolic dish collector shape, not exact shape but imitating one. So the if that is placed on the ground, the same distribution, and make a 3D revolution. So such system in which now this the mirrors also will be like this. There will one flat mirror will be there, one will be there, one will be there. So these can be placed onto the ground. So this particular type of concern, like this particular type of the collector is termed as the parabolic tower, power tower. Okay. So hope these are clear now. So this will be looking at some images related to them. So first is the dish collector, and in which the complete profile will be 3D profile, and this is the immediate this is the pictorial representation for the same. So there will be this dish and the receiver, and here the concentration ratio we can increase up to 1,000 or 1,500 degrees. So there's the same system, like if it is a part of very large parabola, and that is 3D, making it 3D and distributed on the ground. So this similar kind of structure will form. This is a part of power tower. Okay. Now that these are a part of three-dimensional figures. So here for the tracking of the sun, we need to go for the dual axis tracking. Uh, the second category is of the parabolic truck and linear. They are a part of single axis tracking, and generally a term linear parabolic collectors also has been utilized for this, and for them point collector configuration has been set. So this parabolic truck profile is something like this. One parabola will be there, and the receiver section will be there, and it will be excluded in the along the length. Now, if the same system will be divided, if it is a part of very large parabola, the stator profile, if we distribute, cut that and place it on ground, so something like this will form. This is a part of LFR. So then associated what kind application these are generally used has been pointed out in this particular slide. So this is just a brief about like how these concentrator profiles look like and how these configuration has been arrived. So just to summarize with this is once we are running out of time, so I'm concluding with this only the parabolic pitch collector. So it's a kind of the linear the one imitating plant, solar thermal based plant, in which we'll be having a parabolic trough collector distributed throughout the region, and this the complete surface will be termed as an solar field, and this will be the power unit in which the heat transfer fluid will be flown and collected at some particular location, and that is further utilized to generate the steam, and the same is expanded onto the turbine to generate the power from the system. So with this, I am concluding my presentation. Hope I'm able to provide some insights of the configuration. So later on, maybe if any another session, we'll try to move forward.
Any participant want to ask any question?
Any question? So, thank you so much, sir. On behalf of RBCET, I extend a really hearty vote of thanks to Dr. Anish Manan. Sir, spread time from his busy schedule to grace this occasion. Today, we had an opportunity to hear your thoughts, and this will surely be going to encourage our student in future events. Once again, thank you so much, Anish Malan, sir.
Thank you, ma'am. Happy to share my thoughts. And maybe I have limitation of the time, and I will, if time permits, and any another day, we'll be discussing more about that. However, if any of you are not having any doubts as of now, maybe later on, they may write to me. I will share my email address and my LinkedIn profile with Professor Himanshu. The same can be utilized, and I will be happy to help if any of the doubt I may be.
Oh, yes.
Okay, thank you, Dr. Anish.
Yeah, thank you, sir. Thank you very much.
Okay.
Thank you, all participants. Thank you.
Thank you, sir.
Thank you.